Hello. Today we are going to start a new topic called as Laurent's expansion. So let's start this. So we are going to derive an expression for the Laurent's expansion, or we call it as a Laurent series 2. So see this diagram, it's a simply connected region having two circles. This is C1, this is C2. Okay, now Z0 is the center of these circles, and the green line, it's a counter line. The from Z0, that is from center till this circle, it's R. We call it as an outer radius. Then from Z0 to this circle, we call it as an inner radius. Okay, then by Cauchy's integral formula we'll derive f of z. So let me start this. So what is R? R is a inner radius. You can say this is a given part for this diagram. Then R is the capital R is the outer radius. This proof is divided into 3 steps. Drawing this, you can write it as given also. Drawing and imaginary counter line to convert our region into a simply connected region. Okay, so you can say we are starting our proof now by Cauchy integral formula. Integral formula, and for two circles. Which circles we are having? C2, C1. Both are anti-clockwise. C2 and C1 centered at Z is equals to Z0 with radii R2 and R1 respectively. So where in these R is less than R2 is less than R1 is less than R. So what we have by Cauchy's integral formula, f of z is equals to 1 upon 2 pi I close integral for circle C1 f of z dash f dz dash upon z dash minus z minus 1 upon 2 pi I again close integral C2. Same thing will be there, f of z dash dz dash upon bracket z dash minus z. Okay, let me mark this as equation number 1. Now in equation 1 there is a minus sign it is being added, it is being introduced so that the counter C2, that is like C1, is to be transversed in the position, you can say it should be transversed in counter clockwise. Okay, now since for C1 we have Z dash minus Z naught, which is greater than Z minus Z naught, and for C2 we have Z dash minus Z naught is less than Z minus Z naught. This we have defined. Okay. So f of z becomes 1 upon 2 pi I summation of n is equals to 0 to infinity z minus z naught of n close integral c1 f of z dash of dz dash upon z dash minus z naught raised to n plus 1 plus 1 upon 2 pi I summation of n is equals to 1 to infinity z minus z naught of raised to minus n, then close integral c2, then z of z dash minus z naught, this denominator for that previous equation number 1, this is n minus 1 into, it will be f of z dash into dz dash. This I am marking as equation number 2. As I told you at the start, the expression, this proof I have divided into 3 parts. So this is my first part, like this one, this part you can say by Cauchy's integral form. This is the first part. Now this will be the second part. What I'll do, I'll separate this expression as S1 and S2. So now minus sign of equation 1 has been absorbed by the binomial expansion. So as I said, I'll label this, labeling the first series as S1 and second series as S2. Second series as S2. So what we will have, so let me write first, this one will be S1 and this 2 will be S2. So S1 is equals to 1 upon 2 pi I summation of n is equals to 0 to infinity z minus z naught of n close integral c1 f of z dash divided by z dash minus z naught of n plus 1 into dz dash. Let me mark this as equation number 3. Now we will write for S2. Now this one is a regular Taylor expansion which is convergent for modulus z minus z naught is less than z dash minus z naught, which is equals to R1. So that is for all z interior. This is interior, just see this word, interior to the larger circle C1. Okay, now for second series in equation 2 we have value of S2. So this one is S1. So we will write S2. See S2. S2 is equals to 1 upon 2 pi I summation of n is equals to 1 to infinity z minus z naught minus n close integral C2 z dash minus z naught raised to n minus 1 into f of z dash into dz dash. So this will give me equation number 4. Now which is convergent for z minus z naught which are greater than dz dash minus z naught which is equals to R2. That is for all z exterior to the smaller circle C2. Okay, now what I am doing is, as I said, we have the third part. This is the third part of our expression. Does all these series, that is S1 and S2, that is this is S1 and this S2, that is equation number 3 and equation number 4, does two series are combined into one series. We call it as a Laurent series. Okay, so what we are getting, fz is equals to summation of n is equals to minus infinity to infinity a of n equals into z minus z naught raised to n. This is my expression number 5. Okay, so this expression number 5 we call it as a Laurent series or it's a Laurent's expansion. Okay, so what is an here? An is 1 upon 2 pi I close integral C, that is f of z dash dz dash upon z dash minus z naught raised to n plus 1. So I'll mark this as equation number 6. So as this 6, what is equation number 6? So 6 convergence, since equation 6 converges, it's a convergence of a binomial expansion is no longer it's a problem. C may be any counter within the annular region, that is R is less than Z minus Z naught is less than R. So encircling Z naught once in a counter clockwise sense, if we assume that an annular region of conversion does not exist, then the equation number 5 is the Laurent series or Laurent expansion of f of z. That's it for today. So you can see from our today's video that we have drawn a diagram that is just the simply connected region having a radius small r, capital R, and the counter line, and we have two circles C2 C1. So by Cauchy's integral, that was my first part. So Cauchy's integral, we have got this, that is fz is equals to 1 upon 2 pi I close integral this. Then what I have done, we have separated these two terms. So then we have separated these two terms into S1 and S2, and then we have written it in a combined form. So that combined form, it can be represented as f of z is equals to summation of n is equals to minus infinity to infinity a of n z minus z naught to n. So where a of n is equals to this. So as is this is just a 3-step proof, easy to learn and remember. So that's it for today. So thanks for watching.